So in lesson 5.2, we're going to do a review of factoring polynomials. We'll see quadratic ones. We'll also see some other ones. So factoring is a method of expressing a polynomial as a product. So you're going to take a polynomial, sometimes 2 terms, sometimes 3 terms, sometimes more than that, and then figure out what polynomials multiply together to equal that other polynomial. So it's an application of the distributive property. It's kind of undoing multiplying. So it's called factoring, splitting things into factors. The nice thing is once you're finished, you can always check your answers by multiplying it back out using the distributive property or using the idea of FOIL. And lastly, you always want to check to make sure it's completely factored. A lot of directions will say factor completely. So even if you factor, you might even be able to factor a little bit more after you've done one set of factoring. So we're going to work through several different things here as we go through this lesson. So the first thing that we always want to do is see if there's a common monomial factor. So a common monomial factor is a factor of the polynomial common to all the terms. You could have 2 terms, 3 terms, 4 terms, 5 terms, but you want to see if there's a common monomial in each of the terms. So we're going to go ahead and look at this one here. Factor 5x squared y plus 15xy squared. So what we're going to do is we're first going to look at the coefficients. Is there a common factor in 5 and in 15? And we know that there is. 5 goes into both of those. So that's part of our common factor. Now we look at the x's. Here this is an x times x, and then this one is an x. So we have one x in common. And here we have a y and then a y squared. So we have one y in common. So that is our common factor. 5xy goes into this term and 5xy goes into this term. So we are going to say we factor that out. And once we factor it out, we want to think what times 5xy, which I'm going to put here, what times 5xy will give me 5x squared y. Well, we already have the 5. We have an x. We actually need an x squared, so we'll need an x here. And we already have the y, so it's just x. Over here, we have a plus sign. And then 5 times what gives me 15, which is 3. What times x gives me x? Well, we don't need anything, so just a 1. And then y times what gives me y squared, and I need another y. Another way you can think through it is you can take 5x squared y and divide it by the common factor, and you'll just be left with x. Take the 15xy squared, divide it by the 5xy, and you're left with 3y. I mentioned before you can always check this by multiplying. So here's the answer that I think it is. We multiply, that's 5x squared y, what we multiply, and then plus 15, and then xy squared, and that does get us back to our original, so this is our answer. We have some special binomials that we're going to be looking through, actually 3 groups of binomials. The first one is the one that we'll see most often out of those, and it's a difference of squares. If you find something in this form where you have something squared, it doesn't have to be x, it might even be 9, because 9 is 3 squared. So a perfect square minus another perfect square is called a difference, because of subtraction, difference of squares. We're going to multiply this out. This multiplication here, we did multiplying in the first lesson, so x times x is x squared, x times negative y is minus xy, so that's this one, and then y times x is plus xy, and y times negative y is minus y squared. There should be a minus here. These two are opposites, so that becomes 0, and we just have x squared minus y squared. And so we can use this idea to go this direction. If we have an x squared minus a y squared, or a perfect square minus another perfect square, we can factor it into this x plus y times x minus y, or the square root of the first one plus the square root of the second times the square root of first minus the square root of the second. So just a quick reminder, You should know your perfect squares. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared, 5 squared, 6 squared, 7 squared, so that's 11 squared, 12 squared. Some other ones to be familiar with: 13 squared is 169, 14 squared is 196, 15 squared is 225, and you could keep going, but these are the ones that show up a lot. So these are perfect squares. So if one of these is involved in your binomial, it might be that it's a perfect square. So let's come down here. We think, is this a perfect square? Well, yes, it's a times a, so it's a squared minus, and if you want to, you don't always have to write it like this, but we can write this as a squared minus 3 squared, because 9 is a perfect square. Here it is right here. And to factor this, it's simply going to be the square root of a, which is just a squared, which is just a, plus the square root of 9, or 3 squared, so 3. So a plus 3 times a minus 3. So that's a nice simple one. The next one might be a little more complicated. Let's look through it. Remember, from the previous slide, the first thing we should always do is look for a common factor. So we're going to look for a common factor here. Looking at our coefficient, 8 and 32. 8 goes into both of those, so we can factor out an 8. There's an a to the 4th and an a squared, so both of those have at least 2 factors of a, so a squared. And then a b squared, they both have a b squared, so that's a common factor. And now we can think, that, remember there was a couple different ways, told you could think through this. You can actually think of this divided by this, so 8 divided by 8 is 1. A squared, a to the 4th divided by a squared is a squared, and b squared divided by b squared is 1. We don't need to put that. 32 divided by 8 is 4. A squared divided by a squared is 1, and b squared divided by b squared is 1. So that is our factoring out a common factor, but now it says factor completely, so even though we are able to factor out a common factor, we still want to see if we can do something with this. This does fit the form x squared minus y squared, so we rewrite our common factor. Don't forget to rewrite that, and then this is going to be a plus 2, because the square root of 4 is 2, and then a minus 2. So that's our most common binomial, special binomial, the difference of squares. There's going to be 2 more, and these 2 are actually related. So let's go ahead and look at this. A binomial, so this is a difference of cubes, so now we're looking at perfect cubes. A binomial in the form x cubed minus y cubed is called a difference of cubes. A difference of cubes always factors as follows. So if you have a perfect cube minus a perfect cube, it will always be the cubed root of the first, so a minus b, cubed root of the second, and then a squared plus ab plus b squared. Notice this is dealing with our signs that we write. So there's 3 signs here, 1, 2, 3, and the way we can remember those, and because we're going to have a sum of cubes next, and this same idea is going to hold, same, opposite, positive. We say same here because this sign is the same as this sign. Next we say opposite because this sign is opposite of this sign. And then last we say positive because the last one's positive. And that's what's going to happen when we have a sum of cubes also. So let's look at this. Let's go through this. Our perfect cubes, which you should be familiar with. 1 cubed is 1. 2 cubed is 8. 3 cubed is 27. 4 cubed is 64, 5 cubed is 125, and 6 cubed is 216. We could keep going with 7 cubed, 8 cubed, 9 cubed, but these are the ones that we see a lot. Another one I'll throw in here is 1,000. Remember, that is 10 cubed, so maybe we'll see that at some time also. So here we are told to factor this. We want to know, first of all, is there a common factor? There is not. Just 1 goes into both of those, and we don't factor out a 1. So now we think, are these perfect cubes? Is 27 a perfect cube? Yeah, it's right here. It's 3 cubed. m cubed is a perfect cube, and 1, which oftentimes people forget, is a perfect cube. So I'm going to write something here so you see it. When I realize these are perfect cubes, a lot of times what I'll write is just to remind me this is 3m cubed. So this is like my a, and then this is 1 cubed. So this is going to help me when I fill in here. So this is my a, and this is b if we're looking up here at this thing. Let's get rid of some of this extra writing here. And so we can factor this to equal a minus b, so 3m, that's our a, minus b, which is 1, times a squared, so 3m squared, plus a times b, so 3m times 1, which is just 3m, and then plus b, which is 1, b squared is 1. And we should rewrite this because we have this term right here that we can multiply out. So 3m squared is 9m squared plus 3m plus 1. And notice again those signs, same as the original, opposite of the negative, and then positive. So make sure you know this. You'll see in the next slide that we're actually going to have the exact same terms here for the sum of cubes. It's just that the signs will be different. So no a, b, a squared, ab, b squared. So here we go to the sum of cubes. A binomial in the form of x cubed plus y cubed is called a sum of cubes. Can always be factored as follows: a cubed plus b cubed. Notice these things I just did on the last screen. A, b, a squared, ab, b squared. Those are the exact same things as before. It's just that the signs are different, and the signs are going to follow the pattern same, opposite, positive. So very similar, except the signs are different. So we look at this, and that will help us with our signs. So we want to factor this. We have an 8k cubed plus 125 n to the 12th, and we want to know, are these perfect cubes? Well, first, are there any common factors? There are not. So we have 8k cubed plus 125. I'm just rewriting this, n to the 12th. This has one thing that's a little different here. Remember, 1 cubed is 1, 2 cubed is 8, 3 cubed 27, 4 cubed 64, 5 squared 125, and 6 cubed 216. And there are more, so don't just think there's only those. But so are these perfect cubes? Well, yes, this is 2k cubed. And then over here we know 125 is 5 cubed. What about this n to the 12th? What times itself 3 times would give me n to the 12th? And what we can do, that would we can take 12 divided by 3, because we're looking for cubes, is 4. So this is n to the 4th. So 5n to the 4th times 5n to the 4th times 5n to the 4th would give me this. So now that we know these, this is our a, all kinds of arrows all over the place, and this is represents b in here. We can now factor this. So this is going to equal a plus b. So a is 2k plus b, which is 5n to the 4th, times, and remember our signs are same, opposite, positive, so same as this, positive, opposite of this. So I'm going to have a negative here, and then my last sign is going to be positive. Here we put a squared. A is 2k, so we put 2k, and we're going to square that. In the middle, it's a times b, so 2k times 5n to the 4th. And then in the last term, it's going to be b squared, which is 5n to the 4th. The whole thing squared. And so we want to simplify this, try to make it a little neater. 2k plus 5n to the 4th Not a very good 4 to the 4th. 2k, the whole thing squared is 4k squared. Here we have minus, and then 2k times 5 n to the 4th. 2 times 5 is 10. So we have 10k n to the 4th. And then plus 5 n to the 4th squared is going to be 25. 5 squared is 25. And n to the 4th squared is n to the 8th. And there we have the answer. We could multiply this back out if we wanted to show that multiplying this back out will in fact equal a cubed plus b cubed. Let's go ahead and do that really quickly. We're going to multiply here. That's 8k cubed. Multiply here, negative 20k squared n to the 4th. Multiply here, we get plus 50k n to the 8th. And this is looking a little iffy. Like we have these extra terms here, but just wait, those will actually disappear kind of. So we'll multiply here. So we have 5 times 4 is 20, so plus 20, and n to the 4th k squared, or alphabetical order k squared, n to the 4th. Multiply here, we have minus 50k n to the 8th, and then we have this last term. 5 times 5 is 125. N to the 4th times n to the 8th is n to the 12th. And you will notice here, this stays. We just have an 8k cubed. Negative 20k squared n to the 4th cancels with positive 20k squared n to the 4th. And then 50k n to the 8th cancels with this. And we are left with the original. So you see there, when you multiply it out, you do in fact get what you started with. So this here is our answer. You don't have to check every time. I just wanted you to show you that it really does work out that way. So that is factoring. We did factoring the special binomials, the difference of squares, and then the difference of cubes and the sum of cubes.